Neural networks are less prone to vanishing and exploding gradients if you initialize them using Xavier and He initialization. You can also mitigate overfitting issues in neural networks by specifying a regularization parameter. In TensorFlow, how would you specify He initialization and a regularization parameter for each layer of your neural network? In this demo, we'll once again build an autoencoder that works on the MNIST handwritten digit dataset, except that this autoencoder will use regularization to mitigate overfitting our neural network on the training dataset. In addition, we'll also see how we can initialize the weights and biases of our neural network using Xavier and He initialization. I'll skip over the import statements, accessing the MNIST dataset, and our helper function to display a single digit. The show reconstructed digits is the same helper that we've seen before, which displays the original handwritten digit along with the reconstructed output side by side, so we can compare to see how well the reconstruction was carried out. Here are the parameters for our stacked autoencoder neural network. This has three hidden layers. The number of neurons in the third layer is equal to the number of neurons in the first hidden layer. Our autoencoder setup is symmetric. Also, the number of neurons in the input layer is equal to the number of neurons in the output layer. TensorFlow has a built-in library to initialize your neural network weights and biases using the Xavier and He initialization technique. Simply use this library function in tf.contrib.layers.variance scaling initializer. Regularization is also very easy to do in TensorFlow. There is a built-in library for that. If you remember, regularization is one of the ways in which we can prevent overfitting our neural network to the training dataset. Regularization imposes a penalty on more complex models and forces the models to be simpler. The input argument to the regularizer is the regularization rate. This is also something that you can tweak. We start constructing the neural network. The input X placeholder is as before, nothing really new here. Then we set up a partial function for our dense layer specification. This time our dense layer specification has a couple of parameters which didn't exist before. The first is the activation function, that is the LU activation function. LU, which stands for exponential linear unit, is a non-saturating activation function. For inputs below 0, LU has a slight negative exponential value. Every layer of our autoencoder neural network is initialized using Xavier and He initialization and uses the L2 regularizer. Set up the three hidden layers with LU activation, He initialization, and a regularization parameter. The output layer is set up in exactly the same way, except that its activation is set to none. It's a linear layer. Calculate the reconstruction loss in exactly the same way. Because we use regularization to mitigate overfitting our model to the training data, every layer in our neural network has some regularization loss. You can access this regularization loss in TensorFlow using tf.getCollection and specify graph keys as regularization losses. This will give you the regularization losses for all the layers of our neural network. Now, our objective function or the loss that we want to minimize includes the reconstruction loss as well as our regularization losses. So make sure you include both in the loss function. Set up the optimizer and the training operation which minimizes the loss. The loss includes the regularization loss as well as the reconstruction loss. Run for 8 epochs with a batch size of 150. These are all parameters that you can tweak though. Instantiate a session, iterate through all of 8 epochs for every batch with a batch size of 150, and basically run your training operation using session.run. Evaluate and print the reconstruction loss after every epoch and checkpoint your model after every epoch as well. Run the training process on your model and display the reconstructed digit, the original and the reconstructed displayed side by side. And here is what the reconstructed digit looks like with regularization. Just out of curiosity, I'm going to remove the He initialization and the regularization and run this neural network and see how the output changes. Build this neural network once again and start the training process. Once training is complete, first note what the original reconstructed digit looks like. This is the reconstructed digit when we had regularization on, and this is what the reconstructed digit with regularization turned off looks like. Notice again that the background is really granular. It's not just the important features that the neural network pays attention to, it started looking at unimportant details as well. This is a typical characteristic of overfitting on the input data. TensorFlow makes it very simple for you to specify Xavier and He initialization for every layer of your neural network. Set up the built-in library function tf.contrib.layers.variance scaling initializer. This is the Xavier and He initialization, and pass it in as the kernel initializer for every layer of your neural network. Similarly, you can specify a regularization parameter for each layer by instantiating a tf.contrib.layers.l2 regularizer and passing this in as your kernel regularizer parameter for every layer of your neural network.